So 3.1 is exponential functions and their graph. Let's start off with making sure we understand this first model that we're being presented, which is b a to the x. Let's go back to our example of the width of a piece of paper. It's 0.044, that was our initial amount. And then we multiply that, if we doubled it, 2 to the 50th time. In general, if this is our initial value, we label it as b. The rate at which it's exponentially growing is a, and then however many times is x. That's how we get this model right here, where b is in general called a scalar, which is our initial value. Later when we get to word problems related to compound interest, bacteria, growth, radioactive decay, b will be called the principal. A is our rate, our exponential compounding rate, and then x is our input, which is the exponent, and then our output is f of x. So now let's go ahead and look at what exponential graphs look like. So to do that, just like when we're starting out a line, we go ahead and start out with finding outputs for inputs, graph the points, and look at the graph, generalize it. If I plug -2 in for there, I'll go ahead and explicitly do that one. 2 to the -2nd. Think about that as any negative exponents, think like fraction, and you flip it, flip the base, flip the power, turn the exponent positive, and 1 over 2 squared is 1/4. So that gives us 1/4. Next one would be 2 to the -1st, flip that, will give us 1/2. 2 to the 0 is 1. Just to reiterate, side note, y is any non-zero base to the 0 power equal to 1. Well, let's look at, if I have x to the 4th over x to the 4th, you subtract the exponents, gives us x to the 0, or you can think of all of them canceling. That would give us 1. And therefore, anything to the 0 power equals 1. Next, we have 2 to the 1st, which is 2, and then 2 square would be 4. Let's go to graph those to the -2 comma -4th, -1/2, 0, 1, 1, 2, and then 2, 4. You see we have what will look like that. And what happens when we go to -infinity? Well, let's think as x gets very, very small, like -10, -100, and so on. Let's do 2 to the -100th, put as a fraction. I'm doing this upper left-hand corner. Look like that, because I have 2 to the -100 in the numerator. We flip it to the denominator. 2 to the 100 is just an absolutely massive number, and that's still very, very small relative to going to the left down the number line in -infinity. 1 over a very, very, very large number is very, very close to 0, but it would never reach it. So we get this kind of like flattening effect where it, what is called asymptotically, gets closer and closer to that horizontal asymptote. So that's our general graph for an exponential when we're sketching. Later, we have 3 important parts. Let's talk about that. Is this key point right here. We're going to think of that kind of like our vertex of a parabola, the 0, 1. We have an asymptote, horizontal, and then the behavior that goes up like that. Domain is all x values give us outputs. We can plug any value in for x, and we also see from the graph, we draw a vertical line moving left to right. No breaks in the graph, so domain is -infinity, infinity. Sorry, I'm writing with a stylus on my iPad. Kind of sloppy, my apologies. Range down to up. Least value right here is 0, going to infinity. So our range is 0 to positive infinity. X-intercepts is not applicable or none. There are no x-intercepts, never cross the x-axis. Y-intercept is 0, 1. Where is it increasing? If you remember when we're doing increasing, decreasing, we move from left to right. As we move to left to right, the graph's getting bigger and bigger. So it's increasing the entire time from negative infinity to positive. Horizontal asymptote is y equals 0, and then no vertical asymptote. We'll see why all these questions are asked, particularly when we get through the next section. Okay, what happens if we change up? Now let's change up our base to a half. Let's see what happens. Well, if I put a half in, all right, if half is base and I have -2, both those, look at it like that, so it'd be to the -2, so -2 in the -2 and the -2 in the denominator flip to the numerator, which goes 2 squared over 1, which is 4, so it'd be 4. 1/2 to the -1st flipped would be 2. Anything to 0 again equals 1. 1/2 to the first is 1/2, and then 1/2 squared is 1/4. If you look, this is in the reverse order in terms of the outputs relative to what we have in the last one. So now we have -2, 4, -1, 2, 0, 1, 1/2, 2 1/4, and you see we have the same behavior happening, except going not increasing in value but decreasing. Still got a horizontal asymptote because we go off. Think if x gets extremely big, that would just make the fraction value very, very small. And now our domain still negative infinity to positive. Range will be still 0 to infinity. X-intercepts are not applicable. Y-intercept is 0, 1. Now we are decreasing. Note up here, should have been increasing from negative infinity to infinity, but it's more important which one is it, increasing or decreasing. It's decreasing in this case. Horizontal asymptote is y equals 0, and there is no vertical asymptote. Okay, so what generalizations can we make? When a is greater than 1, that's when we have 2. Think of it 3, 4, 5, all the way to 10, even higher. We're going to get that exponential growth. And we're sketching graphs, particularly with transformations. The 3 important key aspects or characteristics in terms of sketching would be that critical or key point, which starts at 0, 1. The horizontal asymptote would be the second part, and then the third part is it growth or decay? In that case, it would be growth. If a is between 0 and 1, like 1/2, then that flips those inputs from positive to negative. Oh, not positive to negative. Flips it from increasing as x gets bigger to decreasing in an exponential fashion. So over here, this is called exponential growth. Those tech advancements that we're talking about have that general exponential behavior to it. Then we also have exponential decay. Just note, when we do have tech adoption, there is a mass adoption point where, like cell phones, like it's pretty much saturated throughout the world for the most part. So get what are called S-curves, look like this. You have very, very little growth, and then you have like mass growth. I think this is kind of like where we're at with like EV vehicles right now. We're like feeling it like changing. And then when it like up here is like, computers, cars, electricity, like, so. But exponential, this has exponential characteristics algebraically to it as well. Okay, so getting back to what we're looking at. There's a lot of interesting things going on with those S-curves as well. Okay, important value, E, it's called natural base right here, 2.71828, 1828, and so on. So I recite E in math, it's that number. It's kind of like saying pi, like 3.14159. A couple others like Planck's constant, gravitational constant. These are just naturally occurring numbers within nature, inherent within the structure of our universe. We'll talk about later sections where E comes from. So generally, what's the differences, similarities and differences between if I graphed e to the x or graph 2 to the x? Well, if I plug in 0, we know what this looks like. This has exponential behavior. Plug 0 into there, I still get 1. And then e squared would be like 2.7 squared, which would be like in the 6s or 7s. And then it's just going to take off just like e. So similarities are, I'm just going to say general behavior of graph, same. still going to have a horizontal asymptote, the same. So horizontal asymptote, exponential growth, and key point, all the same. Differences, outputs won't always be equal, obviously, for the same inputs. Outputs not equal for same inputs. Like if I plug in 2 squared is 4, e to the 2.7 squared, it's basically, it's different value. 2.7 times 2.7 gives something, somewhere in the like 6 range, I think. But in case, the behavior is all the same. Okay, so let's now start looking at transforming, just like we did parent functions going back to the first unit. If I have a +1 right here, that's shifting the graph to the left one. Another way you can think about it, the x0 would give us out an output of 1, and that's like your key point up here. That's that key point right there. So you need 0 to get that key point. Well, here I need a -1 to get that key point. So this point right here has been shifted over 1. So it's a shift to the left, left 1. If I come over to here, that gives us the opposite output, because it's on the outside of the function. So think if I have this, instead of being up positive, it's going to be down negative. So if you look from here to here, that's a reflection over the x-axis, which we talked about in Unit 1, so reflection over x. Negative on the inside is going to flip our inputs from positive inputs. So what was positive gave us this behavior. Now those are going to be negative like this, so that flips it. It's a reflection about the y-axis. It's a reflection about the y. It also makes sense if you look at e to the negative x. If I flip that, if it's over 1 with a negative exponent, we go 1 over e to the x, and now we have 1 over e, which is at between 0 and 1. So that lines up what we talked about with the base being between 0 and 1 and being exponential decay. Excuse me. D, e to the x plus 1, that takes all outputs and moves it up 1. And then here we got a couple things going on. First on the inside we have that +2. Left, I'm just going to write it down here, left 2. And after that, order of operations, negative, so y outputs go from positive to negative or negative to positive. And so that's a reflection about the x-axis, so we got reflection about the x. And then lastly, this 1 is like a +1 in the end, but it's out front, so that just like D, it moves it up 1. Okay, let's see what happens when we have this coefficient out front, and also when we put in a -1 there. And then what we're going to do is, instead of just looking at b a to the x, what if we have these transformations here, the -c there and the +d? What are the generalizations we can make? So then we can reasonably sketch a graph. So let's see what happens here. Well, I know if I plug this in for here, that gave us 1/4, and now that 1/4 is being multiplied by 3, so that's 3/4. For -1 goes in for there, it'd be 1/2, and 3 times a half would be 3/2, or 1.5. If you plug 0 in for here, let's be careful. 2 to the 0 is 1, but then we have 1 times 3, which is 3, so that's interesting. We, instead of 0, 1, we now have 0, 3. Let's see if we can make some generalizations after we get through these two graphs, this one and this one. So now if I plug in 1, 2 to the first is 2, 2 times 3 is 6, and then 2 in for there, 2 squared is 4, 4 times 3 is 12. And let's go ahead and graph those. Zoom in here, see if I can get a little more accurate. Okay, so -2 to the 3/4, -1 to the 1.5, 0, 3, 1, 6, see we're off the graph, and then 2's way up there at 12. It's okay. So I got this exponential behavior, and I think we still will have a horizontal asymptote at 0. I mean, if we plug in a really, really small number like -100 or -1,000, this is going to go to the denominator, so we'll have 3 over this exorbitantly large number. Doesn't really matter if you have 1 over an exorbitantly large number or 3 over an exorbitantly large number. It's going to be overall small number over an extremely large number is close to 0. So we're still approaching 0 as our horizontal asymptote. Okay, so now hopefully we can make, I'll go through input output. Hopefully you see that if we treat this as our parent function, then this function over here is just this all shifted down 1. But I'm still, maybe I'll do a couple of values. Let's look at like -2. Look here, if I plug in -2, I get 2 to the -2, which is 1/4. 1/4 times 3 would be 3/4, but now it's subtracting 1, so just be 1 less than that, which if I did those calculations would be -1/4. And that's just going to happen to all of them, so I think it's safe to say that we can just graph this, where our horizontal asymptote is now -1, and this key point, which was 0, 3, has now been shifted down 3. 1's been shifted down 1, excuse me. And the other ones, the graph's going to still do this type behavior. So yeah, how can we utilize this to help us figure out what A, B, C, and D do? Well, first off, A is our base when A is greater than 1. We know we have exponential growth, and therefore generally when we sketch we're going to have, this sort of behavior. And then when A is less than 1, we have exponential decay, which gives us this sort of behavior. So the 3 important characteristics for full credit for properly sketching an exponential function is the key point, or excuse me, first, since we just did A, sketch it as growth or decay. That'd be the first part. Second part is, where is that key point? Well, if you have no transformations whatsoever, it's at 0, 1. But check this out. In this case, this number out front is 3, and you look, that's what took and made this key point go from 0, 1 to 3. And even when we had this shift of -1 here, you still see the distance between the horizontal asymptote and that key point is still 3. So that's what B is. B is equal to 0, B is, sorry, that I am saying this wrong, my apologies. B is equal to the distance between horizontal asymptote, just putting HA, and key point. That's 0, 1 originally, but if this B value is 2, 3, 4, when you graph your horizontal asymptote, which we'll get to that in a second, that's how far you go from the vertical asymptote to get there. Now, since B is positive, we're going up 3. But if B was negative, that would be a negative on the outside, which flips the graph down. So if I had like a -3 out front here, instead of going up 3, I would go down 3 from this vertical asymptote. C is our phase shift, or haven't used that word yet, sorry, we do that when we get into trig. Horizontal shift. C is a horizontal shift, and we know that because of what we looked at on the last page. We didn't have it here. If you come up here again, if you have, right here, sorry, down at the bottom here, we have this -C. Well, that's inside the parentheses, that's Spider-Man rules, whatever happens. You'd have to plug in C to get that key point. And C is that, so that shifts it to the left or right because of that change of X value like we saw before. And then D is our horizontal asymptote. When D was 0, if you look up here, D is +0, there's our horizontal asymptote. -1 is down here. Now this is something I was going to say, kind of like when I paused earlier, if you noticed. I want to say this and I forgot. Now I remembered again. So why is this -1? How do we know for certain? We know that a -1, the outside Spider-Man rules tell us to shift down, but why -1? Let's look at it numerically. Let's think as x is going to -infinity. If I plug a really, really small number in for x here, again, like to the 100, it would flip -100, excuse me. If I plug -100 and flip it down there, I get that. Now 3 over this exorbitantly large number. Remember, all of this, again, is an extremely small value, which, no pun intended, I guess, is 0. It looks like I circled it. I did circle it, but it looks like a 0 as well. So we get 0 there. But now we have this -1. So we have very, very, very close to 0. Not 0, but very, very close to 0 above -1. So that means as we're going down here, we are some very, very small decimal close to -1. And that's why we have our horizontal asymptote right there. So D is equal to our horizontal asymptote. That's the y equals. So y is equal to D. Okay, so now let's sketch. Determine the key point of the horizontal horizontal asymptote. We know, in fact, I'm going to change this function up just a tiny bit, make it a little more fun here. -2 e to the x plus 3. Yay! I wish I had a little cheering soundbite for making it more interesting. I'm sure you're doing the exact same thing right now. You're like, okay, Mr. Fossey, time to be quiet so I can finish this and get to my assignment. All right, so plus 3 is our horizontal asymptote, so I'm going to put that there. And then the distance from the horizontal asymptote to the key point is 2 in the negative direction, right? So I'm going to go here, and since this is negative, instead of going up to, now if I did this one, I just go up to, and then I graph it. Here I'm going to go down to, boom, boom, and that's going to be at 1. And this is exponential growth. So what I'm going to do is think about if this is, because this is greater than 1, think about this is what it would basically look like if it was up here, but I'm reflecting it, so it's going down like that. And that would be a graph. Lastly, we're going to do some basic solving of equations with variables in the exponent. To help understand this, I gave you this very, very basic equation where you have 2 to the x equals 2 to the third. There's only one value that I can plug in for x, and that would be 3. Right? 2 to the third equals 8, and the only thing 2 to any power that equals 8 is 3, so x equals 3. This is called the one-to-one property. If bases are equal, then exponents are equal. So if we have certain equations, if we can, we are going to aim to get the bases the same and then set the exponents equal. Similarly, if we have exponents equal within, like say if I have x squared equals, let's see, 16 squared, x would just equal 16. But most of these problems, there's other ways to solve that as well, I suppose. But mostly, we're just going to have the variables in the exponent. Okay, so if we look here, I have 2 x minus 2 I'm rewriting. Just doing it to the right here is don't have much room below. 1 over 32, I go, can 32 be written as a power of 2? Yes, it is. 2 to the 5th. 2 times 2 times 2 times 2 times 2 is 32. It's in the denominator, so that would be 1 over 2 to the 5th. Well, I want it to get the same as 2, so I'd flip it from 1 over 2 to the 5th to 2 to the negative 5th, and now we see the exponents are equal. So now you set them equal. X minus 2 equals, x minus 2 equals -5. Add over 2, x equals -3. And we'll be done right there. This model stuff we'll get to in later sections. Hope it goes well. See you all on Friday.